Okay, Assalamualaikum and hi everyone. So today we will continue our discussion on topic 7.1 acids and bases. Okay. So here is the learning outcome. So for learning outcome A, B, C, and D we already discussed. So now we are going to focus on E, F, and G. Alright, so these are the topic. Okay. The first is about pH values of strong acid and strong base. So it's involved the calculation. And then second part is relate the strength of weak acid and weak base with the respective dissociation constant Ka and Kb. And the third part is calculation involving pH, dissociation constant, initial and equilibrium concentration, and the degree of dissociation alpha. Okay. Right. So first part, calculation of pH values of strong acid and strong base. We already know that strong acid and bases are 100% dissociated in an aqueous solution. Okay. So this is the example of strong acid calculation. So the question here is calculate the pH of HCl solution with concentration of 0.02 molar. So the first step, you have to write the dissociation equation. For your information, in the question, this equation, the dissociation equation is not given to you. You must be able to write the equation. Alright, so HCl is a strong acid. So it will dissociate 100%. So that's why you have to use forward arrow. And it will form H plus ion and Cl minus ion. Don't forget to write the phase aqueous. Okay, second step, we have to draw the ice table here. So this is the ice table. So I stand for the initial concentration. C stand for change. You can use the symbol change. Okay, E stand for at equilibrium, concentration at equilibrium. Substitute the initial concentration. Okay, 0.02 for HCl, 0, okay, for H plus and Cl minus because not dissociate yet. That's why it's 0. Change in concentration. Okay, HCl, it will decrease negative X. H plus and Cl minus ion, it will increase positive X, positive X. For the concentration at equilibrium, HCl 100% dissociate, so it becomes 0. Okay, meaning that no more HCl left. It will 100% converted to H plus and Cl minus. So that's why the value of X here is referred to 0.02. Alright, next, our target here, we want to calculate the pH. Alright, so that's why we have to use the concentration of H plus ion at equilibrium. Use the formula of pH equals to negative log of concentration H3O plus. Substitute the values and you will get the pH here is 1.7. Okay, now for strong base calculation. So this is the example of calculation. Calculate the pH of barium hydroxide solution with concentration of 3.5 times 10 power negative 4 molar. So same step. First you have to write the dissociation equation. Right, so remember barium hydroxide. Okay, it is a strong base. So it will dissociate into ion. So that's why you have to use here forward arrow. So it will form barium 2 plus ion. Okay, so 2, remember barium hydroxide is located in group 2. And it will form OH minus ion. Okay, right, since here we have 2 here. So you have to balance the equation first. So that's why you have to times 2. And lastly, don't forget to write the phase. So aqueous. Right, next, draw the ice table and substitute the initial concentration of barium hydroxide. As for the product, is 0 because not dissociate yet. Okay, for the change in concentration, right, so for the strong base, it will decrease negative X. Barium 2 plus increase positive X because the coefficient here is 1. As for the OH minus ion, it will increase since coefficient here 2, so it will increase 2X. Okay, so concentration at equilibrium for barium hydroxide. So it will 100% dissociate. That's why become 0. Okay, barium 2 plus. If this one is referred to X, so X is equals to 3.5 times 10 power negative 4. Okay, because barium hydroxide here is 0. So means X here is the value is the same lah, 3.5 times 10 power negative 4. Okay, next for the hydroxide ion, it will increase 2 times. Okay, so that's why X times 2. And this is the concentration of OH minus at equilibrium. So the question asks to calculate the pH, right? So however, from the ice table, we only have concentration of barium ion, okay, and concentration hydroxide ion at equilibrium. So no concentration of H plus ion. Okay, so therefore you have to use the Kw expression here to calculate the concentration of H3O plus. So Kw is a constant. Okay, so 1 times 10 power negative 14. Substitute the concentration of OH minus, concentration at equilibrium, and you will get the concentration H3O plus. Okay, don't forget to write the unit molar. Okay, now to calculate the pH, use the formula of pH equals to negative log concentration H plus. Substitute the concentration of H3O plus, and you'll get the pH that is 10.85. So what is Ka? So Ka is referred to the acid dissociation constant. So dissociation of weak acid in water, here is the equation. Okay. Alright, so weak acid, when dissociate with water, it not 100% dissociate. So that's why we have to use bidirectional arrow. So this equation is reverse evaporation. So acid will donate a proton to water, and water become H3O plus aqueous, and it will form an ion A minus aqueous. Alright, so since liquid is not considered in the expression, so because liquid constant, so therefore we will get the Ka expression, concentration H3O plus time concentration an ion A minus over concentration weak acid. Okay, right. So for example, HCN, okay, dissociate in water. Okay, HCN is one of the example of weak acid. So it will not 100% dissociate. So you have to use this reversible arrow here. Okay, and then acid will donate proton to H2O plus, and it become H3O plus aqueous, and produce an ion Cn minus aqueous. Alright, so now how to write the Ka expression? So since liquid is not considered, then you will get like this. Okay. Okay, so concentration H2O plus time concentration Cn minus. Remember, it should be concentration of the product divided by concentration of the reactant. Okay. Next, for the base dissociation constant, or short form is Kb. Dissociation of weak base in water. Let's say B is the weak base. When dissociate with water, it will not 100% dissociate. That is why you have to use reversible arrow here. Alright, base, it will accept a proton from water, so and it will become BH4 aqueous and OH minus ion. Alright, so since H2O is liquid, so it is not considered in Kb expression. So therefore we get Kb here, concentration of BH4 plus times concentration of OH minus over concentration of weak base. Okay, for the example here, we have ammonia. Okay, ammonia dissociate in water. not 100% dissociate. That's why you have to use reversible arrow. Okay, and in ammonia, we have lone pair. So, ammonia and nitrogen atom here, we have lone pair. So, it will accept a proton from H2O and become NH4+. And OH minus ion. So, the Kb expression, so for liquid is not considered, so therefore you will get Kb expression like this. Remember, concentration of the product divided by concentration of the reactant. For strong acid and strong base, it's 100% dissociate. So that's why Ka and Kb values have not been measured. Okay, no Ka and Kb for strong acid and strong base. Alright, so these are Ka values for some monoprotic acid. Okay, monoprotic acid, and for Kb value of some molecular. So usually amine, so which refer to base. Okay, so you can see that the Ka values increase. Okay, so Ka value increase will indicate that the acid become more stronger weak acid. Okay, as for the Kb here, it will increase. Okay, which means the weak base is a stronger base. Okay, so strong acid, which means high percentage of dissociation. Okay, so it will get higher concentration of H3O+. That's why we get larger Ka. So larger Ka, stronger weak acid. Okay. Next, a stronger base, okay, which refer to the high dissociation, okay, of weak base. So it will form higher concentration of OH minus. So therefore, you will get larger Kb. So larger Kb, so stronger weak base. Right. So now, relationship between Ka and pKa. So pKa is equals to negative log Ka. So P is stand for negative log. Alright, so Ka is high. When Ka is high, then you'll get the value of pKa become low. Okay, so we can see example here. Okay, so if the Ka is high value, then you get the value of pKa become lower. Okay, so which means that larger Ka means higher acidity. So more acidic. Okay, next for the relationship between Kb and pKb. So pKb is equal to negative log Kb. So if the Kb value is high, so therefore the value of pKb is low. Okay, for example, like methylamine has the biggest value of Kb. So therefore, it will have the value of pKb is the lowest. So larger Kb, which means that the solution or the weak base is a stronger base. Right. So this example of question that relate between the pKa and Ka. Alright. So based on the given pKa values, which acid is stronger? So we have two between ethanoic acid and methanoic acid. Which one is the strongest? And the value is pKa is given here. So remember, if Ka is high, which means pKa is low, so the concentration of H plus high. So we will get the value of pH become low. So that's why it's become more acidic. So which means for this one, which one is the strongest? So refer to the pKa values, and you have to choose the lower pKa values. Okay. So therefore the answer here. Alright. So methanoic acid is stronger than ethanoic acid because it has smaller pKa values. Okay. Right. So for the second question, based on the given pKb values, which base is stronger? Alright. So we have two here. This is aniline and this is ammonia. Given to you the pKb value. Right. So remember Kb high, which means we'll get pKb low. Okay. Then you get the concentration of H plus become low and pH is high, which means the solution is more basic. So for this example, you have to choose pKb value the smallest. So which means NH3 is stronger than aniline. So for this one, you must be able to write acid dissociation equation. So remember, an acid donate a proton to weak base and form H3O plus and an ion. For example, like HCN dissociate in water. So HCN donate H plus to H2O and become H3O plus and release Cn minus ion. So this one, ethanoic acid dissociate in water. Okay, so it will release H plus. Okay, H plus from COO minus ni. H plus here. Okay, so it will release H plus here. This H. And it will form CH3COO minus and H3O plus. Okay, so nitrous acid HNO2. So it will donate a proton to H2O and become H3O plus and release NO2 minus ion. Okay, so how to write a base dissociation equation? So when a proton is accepted by a weak base contain nitrogen atom, so the H plus bind to a lone pair of electron on an atom of the base. Okay, usually for the weak base, usually it contain nitrogen atom. For example, like ammonia, okay, dissociate in water. So ammonia have lone pair, so it will accept a proton from water and become NH4 plus. Okay, and then OH minus ion. Okay, same thing goes to this. Okay, right. Okay, so a nitrogen atom have lone pair, will accept a proton from H2O and the number of hydrogen atom it will increase, so become N2H5 plus. Okay, because accept a proton and OH minus. Right, so for this example number 3, so focus on nitrogen. Nitrogen here we have lone pair, accept a proton from H2O and the number of H attached to nitrogen it will increase and become 2. Okay, and the charge here is positive and produce OH minus ion. Okay, so weak acid and weak base equilibrium problems. So we have two types. The type 1 here is a given equilibrium concentration. Then you have to calculate Ka and Kb. Okay, for type 2, given Ka or Kb and some concentration information. And then we have to find out equilibrium concentration. Equilibrium concentration. Alright, so for these two type of problem, so you have to use ice table. Okay, for example, for type 1, type 1. Okay, so the pH of 1.0 molar solution of monoprotic acid is 3.5. What is the dissociation constant for weak acid? Which means we want to calculate the value of Ka. Okay, what should you do? Right, so first you have to write the general dissociation equation. Okay, for monoprotic acid. Monoprotic acid means it has only one H. Okay, HA dissociate become H plus and A minus. Right, so it will become H3O plus. So water it will accept a proton from weak acid become H3O plus and A minus. Okay, second step, draw the ice table and substitute the values of initial concentration. That is 1. Okay, as for the H2O, this is in liquid, not consider. So just draw dash, dash, dash. Okay, H for the H3O plus and A minus is 0. Okay, is 0, which means not dissociate yet. For the changes, weak acid, this will decrease, negative X. H3O plus increase, A minus also increase. So for the weak acid, it is not 100% dissociate. That's why in the equation here, use reversible arrow. And the concentration at the equilibrium, so it's not equal to 0, because not 100% dissociate. So at equilibrium, concentration of weak acid is 1 minus X. Concentration H3O plus and A minus is X. Okay. Now, our target, we want to calculate the the Ka values, which means you have to calculate the concentration at equilibrium here. What is the value here? So now we have to solve the value of X. Okay, what is the value of X here? Since in the question is already given to you the pH, that is 3.5. And we know that the formula of pH is negative log concentration H plus. Okay, from here we can find out the concentration of H plus. So concentration H3O plus is referred to X times with negative 1 both sides. So we get negative 3.5. And then you have to both log from the left side to the right side. So it will become anti-log. Okay, so anti-log actually is 10 power of negative 3.5. Press your calculator and you will get the concentration of H plus ion is 3.1622 times 10 power negative 4 molar. So actually this is the value of X. X here. Alright, so next you have to write the Ka expression. Okay, so since right here this is liquid, H2O liquid is not considered. So therefore you get Ka expression, concentration H3O plus times concentration A minus over concentration HA. Substitute all the values. X here is referred to this. Okay. And then for the concentration of HA, right? So 1 minus X. Okay. Right. So finally you will get the Ka value here is 1 times 10 power of negative 3. And remember Ka no unit. Okay. No unit. Alright. Next we move to the second example. Question asked to calculate Kb. Given to you the concentration of ammonia 0.55 molar and also given to you the pH 11.5. Alright, so what should you do first? You have to write the base dissociation equation. Alright, so ammonia dissociate in water, not 100%. That's why we have to use reversible arrow. So ammonia accept a proton. So that's why we become NH4 plus and OH minus. Second step, draw the ice table and substitute the initial concentration. That is 0.55. As for the liquid, it's not considered. Okay, because it is constant. Just write dash, dash, dash. As for the product, 0. Okay, because not dissociate yet. Okay, for the change, ammonia, it will decrease, negative X. Product, it will increase. Okay, as for the concentration at the equilibrium, since NH3 is a weak base, so it will not 100% dissociate. That's what 0.55 minus X. Okay, as for the product, X. So question asks here to calculate the Kb. So actually, we want to calculate all the concentration of the species at equilibrium. So how to solve this? Okay, because we have one more information here, refer to the pH. So therefore, you have to use the calculate the pOH. Since here in the ice table here we have OH minus ion, so that's why you have to calculate pOH. Okay, so that we can calculate the concentration of OH minus ion. So when you calculate, you can use this formula, pH plus pOH equals to 40, and you will get the pOH value is 2.5. Right, next, using the pOH formula, negative log concentration OH minus, you can find out the concentration of OH minus. Okay, so that is 3.1623 times 10 power negative 3 molar. That is referred to value of X here. Okay, next, write the Kb expression. So H2O is not included because it's liquid. So next, substitute the value of X here. Here it becomes X squared. Okay. So because this is X, so that's why it becomes X squared. So for the concentration of NH3 at equilibrium, 0.55 minus X. And finally, you'll get this 1.83 times 10 power of 5 negative 5. And remember, Kb also no unit. Okay, next, for type 2 calculation. Before that, there are a few things that you have to consider, right? So you have to focus on the value of Ka or Kb given. Alright, so the first case, if Ka or Kb is less or equal to 10 power of negative 5. So the concentration of H3O plus from auto ionization of H2O is negligible. So therefore you can use the approximation method. Okay. So which means you can assume, okay, a weak acid or base has a small Ka or Kb. So therefore we can assume initial concentration minus change in concentration is approximately to the initial concentration, since the changes is very small. Changes here is referred to the X. X value is very small. Right? So therefore, it's approximately to the concentration of the initial. Okay, for the second case, if Ka or Kb is equal to 10 power of negative 1 or 10 power of negative 2 or 10 power of negative 3, so you cannot apply the approximation method. Right? So you have to calculate the changes in concentration that is referred to the value of X by using quadratic equation. And only choose the positive values because X is referred to the concentration at equilibrium. Okay, for the third case, if Ka or Kb is equal to 10 power of negative 4, so you have to apply 5% test to check the assumption is justified. Okay, so if the 5% test is referred to the change in concentration over initial concentration. If the ratio here, okay, ratio of change in concentration to initial concentration is bigger than 0.05, so therefore the change in concentration, which refer to the X value, you have to calculate using quadratic equation. Okay, so if the 5% test, the ratio of change in concentration to initial concentration is less than 0.05. Right? So meaning that the change in concentration, the value of X, you can calculate using approximation method. So what is approximation method? So we will discover after this. Okay. Right. So degree of dissociation, also known as degree of ionization, is referred to the ionized acid concentration at equilibrium over initial concentration of acid, and percentage dissociation is referred to the ionized acid concentration at equilibrium over initial concentration of acid times 100%. Okay, so here is example number 3. Alright, so example 3, so a solution of nitrous acid, okay, has a concentration of 0.036. Calculate the pH and then given to you the Ka value. Ka value is already given. So what should you do first of all? Okay, so first of all, you have to write the dissociation equation. Okay, so HNO3, so it will donate a proton to H2O and it will form H3O plus and release NO2 minus ion. Then you must include the phase also. Alright, next, okay, draw the ice table and substitute the initial concentration of HNO3, that is 0.036. As for the H2O is in liquid, is not considered. So you have to just write dash, dash, dash. Okay, concentration of H2O plus and NO2 minus is 0 because not dissociate yet. Okay, for the change in concentration, for HNO3, it will change a negative X, decrease negative X. Okay, H3O plus, positive X, NO2 minus also positive X. So since HNO3 is a weak acid, so it will not dissociate 100%. It will dissociate partially. So therefore at the equilibrium, okay, the concentration of HNO2 is 0.036 minus X. Okay, as for both product is X. Okay. Alright, so for the next step, write the Ka expression. So H2O is not included in the Ka expression. So you will get like this. Remember, concentration of the products over concentration of the reactant. Substitute all the values which refer to the concentration at equilibrium and the Ka value 4.5 times 10 power negative 4. Right, so let's say we assume, because this is 10 power negative 4, let's say we assume the concentration X is very small. X here is very small, smaller than 0.036. So we can assume that 0.036 minus X is approximately to 0.036. Okay, so and then substitute, and then you get here X squared equals to 4 times 10 power negative 4 times 0.03. So times. Okay, and then we get the value of X here. 4.025 times 10 power of negative 3. So because here is 10 power negative 4, so you have to test. You have to apply the 5% test to check the assumption is justified. So meaning that whether this assumption can be used or not. Okay. Right. So when you apply 5% test, that is referred to the changes in concentration over initial. So changes here is referred to the value of X here over to the initial 0.03, and then you get here 0.112, which is bigger than 0.05. Alright, so since we get here the 5% test here is bigger, okay, bigger. So therefore the approximation method cannot be applied. So we cannot apply this. Okay. So that's why you have to solve by using quadratic equation. Right? Alright, so you calculate until you get quadratic equation. This is A, so this is B, so this is C. And then just press your calculator and you get two values of X. Right, so and we notice that X1 is positive value, X2 is negative value. So therefore, we only accept X1 and X2 negative value is not accepted because X here is referred to the concentration at equilibrium. So concentration cannot be negative value. Right, next, use the value of X1, substitute into the pH formula. So the same question asks to calculate the pH. Right, substitute here, then you get the pH of the solution is 2.42. Right, next, for example, number 4. So, given to you the solution. Okay, HF has a concentration of 0.5 at 25 degree of Celsius. Alright, and then you have to calculate the equilibrium concentration. Okay, H3O plus and equilibrium concentration for F minus ion, the pH of the solution, and the degree of ionization of HF. Also given to you the Ka value, that is 7.1 times 10 power negative 10 negative 4. So first of all, what should we do? So you have to write the acid dissociation equation. So HF, weak acid, donate a proton to H2O and it will form H3O plus and F minus. Alright, next you have to draw the ice table. Okay, so substitute the initial concentration. So it's already given 0.5. Okay, as for the H2O liquid, it's not consider. Just write dash dash dash. H3O plus and F minus is 0. Okay, because not formed yet. Okay, for the changes, HF it will decrease negative X. H2O increase. F minus also increase positive X. Okay, concentration at equilibrium. So for HF 0.5 minus X. For H3O plus is X. F minus also X. Alright, next write the Ka expression. So H2O is not included in the Ka expression. Substitute all the values according to the concentration at equilibrium. So, and also the value of Ka. Right, next, assume, make an assumption. Okay, so let's say X is less than 0.05. So therefore 0.5 minus X is approximately to 0.5. Then you get like this. Okay, which means X is very small. Okay, so next, find out the value of X. X is 0.01884. Alright, so because the given to you the Ka value is 10 power negative 4, that's why you have to apply the 5% test in order to check whether the assumption can be used or not. Assumption is justified. Alright, so therefore substitute changes over initial concentration. Okay, then you get 0.03768. So which is smaller than 0.05. So because of that, so the approximation method can be applied. So here we can apply this. Okay, can be applied. So therefore, we can use the value of X here. Okay, question A asks to calculate the concentration of H3O plus at equilibrium. That is referred to X. So therefore, 0.01884, and then forget the unit here is in molar. Alright, so question B asks to calculate the concentration of F minus at equilibrium, also referred to X. That is 0.01884 molar. Okay, for C, calculate the pH. So use the formula of pH equals to negative log concentration H3O plus. Okay, then you get 1.72. And D, degree of dissociation. So it's referred to alpha. Okay. Ionized acid concentration at equilibrium. Ionized here is referred to the value of X over initial concentration. So X here is 0.01884 divided by initial. Therefore, you get here 0.0376. Okay, for the next question, example number 5, a solution of hydrazine HN2H4 has a concentration 0.025. So you have to calculate the pH of the solution. Okay, and what is the percentage of this ionization? And given to you, the Kb value here is 1.7 times 10 power negative 6. So negative 6 is bigger than negative 5. Okay. So the first step, what should we do? So you have to write the base dissociation equation. Okay. So how that you get this equation? So we know that nitrogen have lone pair, and nitrogen it can accept a proton from H2O. So that's why it become number of hydrogen attached to the nitrogen become greater. So become like this too. And positive charge. Right. Since H2O is donate a proton to nitrogen. So it will become OH minus ion. Alright, next, draw the ice table and substitute the initial concentration, that is 0.25. Product is 0, not formed yet. Changes, right turn, negative, decrease. Product will increase. Concentration at equilibrium for hydrazine, 0.25 minus X. Okay, as for the product, X, increase. Alright, next, write the Kb expression. So H2O liquid is not included in Kb expression. Substitute all the values at equilibrium. Okay, and then because this is negative 6, it's less than 10 power negative 5. Right, so therefore we can apply the approximation method. Okay, so 0.25 minus X is approximately 0.25. Okay, substitute and then find out the value of X. Right, so actually value of X here is refer to the concentration of OH minus ion. Alright, so next question asks to calculate the pH. However, from the ice table, we only have the concentration of OH minus ion. So therefore, before we calculate the pH, you have to calculate the pOH. Okay, because in the ice table is not include the concentration of H3O+. So calculate pOH by using formula of negative log concentration OH minus. Then you get the pOH value is 3.19. Alright, so next, by using formula of pH plus pOH equals to 14. Alright, substitute the value of pOH, that 3.19. Then you get the pH value is 10.81. Alright, next, for the percentage of ionization, first we have to write the formula. Okay, X changes over initial concentration. Changes here is referred to X. Substitute value of X over initial, 0.25 times 100%. And then when you calculate, then you will get 0.26%. Okay, I think that's all for today. Okay, hopefully you can try to answer the tutorial 7.1 F. Try to answer and we will discuss in the next lesson. Thank you and Assalamualaikum.